Hello. This is the official tutorial video for the Zooming SlowMo 4 Microscopy notebook. The notebook consists of 8 different sections, of which the first 2 sections provide you with the general information about the capabilities of the tool, the source of the original implemented paper, links to some tutorial videos, and general information about the handling of the Google Colab environment. In the section 0.0, before getting started, it points out some of the limitations of this Google Colab environment. Please read through this and the previous section in detail to avoid common mistakes. Through the course of this tutorial video, we will go through each of the following sections 1 to 6 in more detail. Please follow along. First, we need to connect the notebook to the Google Colab server. Press the Connect button at the right-hand corner. In section 1.1, you can check whether you have access to a GPU, which will be necessary to run this notebook correctly. If no GPU is available, you can go to Runtime, change runtime type, and set up the hardware accelerator to GPU. Next, you can connect to your Google Drive data by running this cell. You need to press the URL link in the browser. This will open a new tab which lets you connect with your Google account. Then copy the code and paste it into the authorization code cell and press Enter. Your Google Drive folders will appear in the Files section on the left side of the Google Colab notebook, and you can navigate to any folder that is stored in your Google Drive. By right-clicking a selected folder, you can copy the file path to that folder, which will be helpful in the following sections. Similarly, you can connect to your Google Cloud bucket from your Google Cloud Storage by providing the project ID and the bucket name in this cell. Before running the cell, you also need to change the bucket name to your bucket name in the second last line of this code cell. By double-clicking on the text, you can enter and close the code cell within the Google Colab environment. Next, you need to install the necessary requirements for running the Google Colab notebook by running the first cell in section 2. This may take several minutes to finish. After finishing the installation, the Google Colab runtime will automatically reconnect to load the necessary libraries that were downloaded in this step. If after the installation process the files folder that disappear, you can just refresh the website, which solves this problem. After installing the necessary Python modules and the necessary GitHub repository for the Zooming SlowMo 4 Microscopy notebook, a new folder called Zoom Interpolation will appear in the Files section on the left-hand side. In this folder there's also a demo folder with some test files, which we will be using to test the notebook in this tutorial. When doing your own experiments, you can change the file path from the demo folder to your own data that you will be using. The second cell in section 2 just avoids Google Colab to disconnect, in case if you need to do some preparatory steps for your images. This cell will run for 1.5 hours without Google Colab disconnecting, but can be stopped at any moment to continue with your work progress. In section 3, images can be manipulated and prepared for the notebook. This is mainly helpful for the quality evaluation step in section 6, where the downsampled and downsized images, which are re-upscaled and reinterpolated with a neural network, can be compared with the ground truth images. The first cell in section 3 converts CZI files into TIFF files, which is the necessary file format for this notebook. The next cell allows to display the image dimensions of a selected image TIFF file. The third cell in section 3 reduces the image size by a given downscale factor of the images in the selected folder and creates a new folder with the new downscaled images. If you use 5DTZXYC image files, please check the use_RGB ticker. The next cell can produce bilinear or bicubic upscaling. If you use 5DTZXYC image files, please check the use_RGB ticker. The fifth cell can scale down the image frequency by a given factor in Z, T, or both dimensions. The cut target frame number limits the number of frames in the output files. Section 4 prepares the training data for the network. If you have small datasets for fine-tuning the network, you can run the cells in this section to prepare the data. If you want to prepare bigger dataset larger than 7 to 10 gigabytes, we recommend you to use the Python scripts on your computer provided in the following folder. You can upload the LMBD files to Google Colab via Google Drive or Google Cloud Storage and load it in the training stage. Otherwise, just provide the information of the source path, the scale factor and the input dimensions of the high-resolution images and run the cell. Then a new folder will be created that will be called out_HR_LR, where you will find a high-resolution and low-resolution LMBD folder. Sometimes the preparation step fails, which can be tested in the cell 4.2. If it throws an error, the preparation step needs to be repeated or carried out offline. After preparing the training folders, the training or fine-tuning of the network can be carried out. If the data was prepared offline, the folders after uploading can be selected in the Train LMBD HR and Train LMBD LR cell. The scale factor needs to be provided and the low and high resolution dimensions of the provided training data as well. The editor cell determines how long the network will be training. The Save Checkpoint determines after how many iterations the network will be saved as a checkpoint. In the backup location, a folder on your Google Drive can be selected to make sure that the training results are not lost. The learning rate can be selected here. For fine-tuning, it is recommended to use a very low learning rate, otherwise the weight will get disturbed too much and the performance will drop instead of increase. The warm-up_iter cell tells how many iterations it will take to gradually approach the selected learning rate. After the training is finished, running cell 4.3.2 will update the model in the folder with the last saved one from the training. Sometimes it is worth checking which of the trained backup models had the best accuracy to manually select that one and exchange it in a pre-trained models folder. The results of the training can be visualized in section 4.3.3. If you want to see the training of an old model, you can also manually provide the path to the saved folder of the older network. After performing the training, we can use the network to perform the resolution and frame interpolation on our test dataset in our demo folder here. Here we select the previously downsampled and downsized image to be able to compare it later with a ground truth. We need to select the input pixel size of the files in that folder. We need to select in which dimension we want to perform the interpolation. In T or Z or both dimensions, and if we want to perform also the resolution upscaling as well. For this we can select the zoom factor. For zoom factors greater than 4, the network will be used twice. Finally, you can provide the folder where the frame rate and resolution enhanced file should be stored. After running this cell, a new folder will appear with the enhanced image. It can be downloaded from the files, or if saved on your Google Drive, it can be downloaded from your browser. In image J, the dimensions can be reordered to get the enhanced image. In the final section, section 6, we can compare the enhanced images with the ground truth images to get an idea of how well the network performed in the two enhancement tasks. The first cell checks if the image pixels got shifted during the interpolation or upscaling step. Here you should select a slice that you want to compare the ground truth and the interpolated image sequence. It should be an uneven slice because the even slices are the same for the ground truth images as for the interpolated ones. It should be an uneven slice because the even slices are the same as the ground truth images as the interpolated ones. In case of a multicolor image, you should also select the channel that you want to evaluate. The second cell evaluates the image and saves two CSV files, which shows the mean quality values, and the other one shows the quality values for each slice. It also saves the SSIM and RMSE maps of the dataset in the same folder. Finally, the third cell shows you SSIM and RMSE maps of a selected image slice which you can select in the Z dimension and T dimension cells. If you found out in section 6.1 that the image got shifted, you can also correct the shift by manually selecting the pixel shift here. Furthermore, it provides the RSNR, MRSE, and SSIM values for this specific image slice or frame. This was the demonstration of the Zooming SlowMo for Microscopy notebook. If you want to use your own images, just make sure that they are in the right format and right bit depths. And then you can use them from your Google Drive folder and just exchange the source_path in the notebook. I hope you find it helpful. Good luck.